as I mentioned earlier, Taylor series are infinite, and we're using computers to approximate quantities in this course. So realistically, we're not going to use an infinite Taylor series. We're going to use a truncated version of the Taylor series where we only go up to a certain degree for the polynomial. So in other words, we're looking at finite Taylor polynomials now instead of infinite Taylor series. So the definition for this is very similar to Taylor series, and we will continue to work with Taylor series still, even though I'm saying the Taylor polynomials are more useful for computing, but that's just so that we can really understand the ideas behind a Taylor series and then use those ideas to apply to the case of Taylor polynomials. So the definition of the nth degree Taylor polynomial of f of x about x equals alpha is given by the formula t sub m of x, so that just indicates the degree, equals the sum from n equals 0 to m of the nth derivative of f evaluated at alpha over n factorial times x minus alpha to the n. And this definition only holds when this polynomial exists. There might be a case where, your function doesn't have enough derivatives, or your function doesn't have a degree m term or something. So we'll handle those special cases as they crop up. But in general, this is the definition we'll work with, just keeping your eyes open for cases where this definition might fail. So we're going to work through some more examples. And the next example we're going to work through is finding the 68th degree Taylor polynomial for the Taylor series that we found in the last example. So that was a Taylor series for e to the x, centered at x equals 101. And we found that that series was the sum from n equals 0 to infinity of e to the 101 over n factorial times x minus 101 to the n. So if you are looking at the PDF for this Taylor series review, there are questions on these finite Taylor polynomials on this page and on the next page. So I would encourage you, again, to pause this video right now and try the problems. And if you get stuck or if you finish, come back and watch the video and check your work against these solutions. So pause it right now. Okay, so the solutions. First, the solutions for this Taylor series for e to the x. The 68th degree Taylor polynomial exists in this case because all the derivatives of e to the x exist, and there's no zero coefficient, so all of the terms appear in this sum. So for this answer, we simply write that T68 of x is the sum from n equals 0 to 68. So all we're doing is changing the 68 to infinity, changing the infinity to 68 in this case, of e to the 101 over n factorial times x minus 101 to the n. The next question asks what the values for C0, C1, and C50 are. So these are just the constants that lie in front of the x minus 101 to the n for each term. So C0 is just e to the 101 over 0 factorial. And As a refresher, remember that 0 factorial is equal to 1, so this just simplifies to e to the 101. Similarly, C1 also simplifies down to e to the 101. C50 is e to the 101 over 50 factorial. And you should never try to simplify factorials, just leave them as 50 factorial or whatever. I guess I shouldn't say you should never try to simplify factorials, but please, please, please do not do something like calculate 50 factorial and write it down as a solution, because that just causes yourself and myself pain. So leave the answer in this form. And last, Cn is the term e to the 101 over n factorial, and that holds for n bigger than or equal to 0. It is very important to specify the range for n here, because when you're doing math, you want to be very specific about what you're doing and what range you are working with. So if you ever write the answer for what a C sub n is, you should make sure to include the values for n that are associated with it. This next example is more complicated, so if you didn't get it or had some confusion, that's totally reasonable. So in this example, we are looking at the Maclaurin series for f of x equals cosine of x. And just recall that when we say Maclaurin series, we are just specifying that we're expanding around the point x equals 0. So our alpha is equal to 0 in this case. And here I give you the series. The series is equal to the sum from n equals 0 to infinity of -1 to the n over 2n factorial times x to the 2n. This probably seems odd. It doesn't really fit the format of the previous Taylor series you have seen. And we can go over the derivation of this at some point later. But for now, just accept that this is the series and don't necessarily worry about how this series is derived. Unless you want to for fun, then you're welcome to. So our series is given by this formula -1 to n, x to the 2n over 2n factorial. And we're just going to plug in the first few values of n to see what this series looks like. So if we plug in 0, we have -1 to the 0, x to the 0 over 0 factorial. If we plug in 1, the next value of n, we get -1 to the 1, but then it's x to the 2n, so that's x squared, because 2 times 1, over 2 factorial, because again, we have 2n. Then the next term is -1 squared, we're plugging in n equals 2, times x to the 4th, because again, the exponent is 2 times n, over 4 factorial, and so on. So if we simplify this, what we get is 1 for the first term, because anything to the 0 power is 1, and 0 factorial is 1. Then we get minus, since the -1 is raised to the first power, we get minus x squared over 2 factorial plus x to the 4th over 4 factorial. So that's what we get if we simplify the series that we just saw, where we wrote out the first 3 terms for n equals 0, 1, and 2. But we can see a pattern emerging, and the pattern emerging is that we're doing the even exponents, and every other term is subtracted and every other term is added. So we have 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial, and then it will continue in this manner with minus x to the 10th over 10 factorial plus x to the 12th over 12 factorial, and so on. So the first question asks us why does the third degree Maclaurin polynomial not exist in this case? So a third degree polynomial is a polynomial with an exponent of 3 as the largest exponent. There's no degree 3 term here. We only have the even degree terms like 2, 4, and 6. But if we look, there's no x to the third. So since there's no x to the third in this series, we don't have a third degree Maclaurin polynomial. However, the next question asks what the fourth degree Maclaurin polynomial is, and we do have that. It's the computation we made initially, where we went up to x to the fourth. So this polynomial is 1 minus x squared over 2 plus x to the fourth over 4 factorial. You may notice that I said 2 instead of 2 factorial. They're the same. 2 equals 2 factorial equals 2 times 1. So sometimes I'll just shortcut and say 2 instead of 2 factorial, or 1 instead of 1 factorial, and so on. So anyway, that is the start, or that answers our first two questions. The next question asks what Cn is equal to, and this is a little bit trickier. So the next question about what Cn is equal to is also a little bit tricky, and that's just because of the way this Taylor series is written to be in a compact form, using the exponent of 2 times n and the 2 times n factorial in the denominator. So we have to pick it apart a little bit in order to understand this. So think of Cn as the coefficient for the degree n term. So C1 should correspond with the coefficient for the degree 1 term, which we know there is no degree 1 term. So C1 is 0, C3 is 0, C5 is 0, because we don't have odd degree terms. And then for even degree terms, Cn should correspond with the coefficients that are present, which are -1 to some power over the degree of the term factorial. So it would be wrong to write your answer like this. It would be wrong to just say that Cn is equal to -1 to the n over 2n factorial, because then we are associating the coefficient Cn with the 2nth degree term. So they're not the same, and we have to work with this a little more. So the correct way to write this is actually as a piecewise function, where we say that Cn is 0 if n is odd, because we know the odd degree terms do not exist. And then, if n is even, we're going to say that Cn is equal to -1 to the n over 2 divided by n factorial. So you'll notice I'm taking the terms of the expression in our Taylor series, and I'm dividing them by 2, because the Taylor series associates n with the 2n degree term, and we want Cn to be associated with the nth degree term. So in order to have it associated with the x to the n term, we have to take that x to the 2n and divide the 2n by n. And thus we divide all of the n's by 2 as well to make sure it all matches, and we get this expression here. So if you wanted to work some of these terms out to understand why this piecewise function is the answer, you certainly should. So I'll work out the first few for you. First of all, C0 is just -1 to the 0 over 2 power divided by 0 factorial. So of course 0 over 2 is just 0, so we have -1 to the 0 power over 0 factorial, which is 1. So 1 is our coefficient of our first term, of our degree 0 term, so that makes sense. if you look back at the Maclaurin polynomial that we wrote out earlier. Now, C1 equals 0 because 1 is odd, and that is consistent with the polynomial we looked at earlier. And C2 is equal to negative 1 to the 2 over 2. So that's negative 1 to the 1. And if you look back at the polynomial, you'll see that the x squared term did have a negative 1 to the 1 in the numerator. And then the denominator is going to be 2 factorial. And again, if you look, you'll see that the x squared term had a denominator of 2 factorial. So if you're not convinced yet, go ahead and work out C3, C4, C5, and so on using this formula. And then just check if, C3 has the same coefficient as the x cubed term, C4 has the same coefficient as the x to the 4th term, and so on, in order to convince yourself that this formula is correct, because it's a little odd the way we're doing this, dividing the n by 2 when we're writing this piecewise function.